All right, so welcome to my talk. I called this talk not just a bunch of random letters, but pretty close. And you'll get this shortly, but it's kind of a running joke in terms of what eBPF stands for. Does anyone know what eBPF is? Oh, geez. All right, I'm done. I'm just gonna go home. Yeah, so it stands for Extended Berkeley Packet Filter, and it's kind of a misframing of the acronym now because it's really gone so much further with the project, and we'll talk about this more. So just to introduce myself, my name is Sean Pitts. I work at Grafana Labs. I'm a technical marketing engineer there. I live with 7 dogs. I have 2 beagles, 3 wiener dogs, a pug, and a foxhound. Something I actually do for myself is I make YouTube videos. I have a YouTube channel, which is why I'm filming this right now. And then also I just love to learn and try to understand how things work, especially eBPF. And the key word there is try. But before we talk about like what eBPF is, I show you guys like things you can do with it. What I want to talk about is the history of eBPF because the story is actually really cool. Has anyone ever seen the documentary that they posted on eBPF? All right, awesome. Before we get started, who knows what this is? I'm going to call on somebody, so if you're confident, or speak up, just speak up. What is it? SDN, correct. And that is really how the eBPF project got its start, right? So I don't need to like explain what SDN is to most of you smart individuals, but it really is sort of this revolutionary way that I think when SDN started, which I was probably like 12 years old, so I can't even say like, hey, I was working with SDN. I think like when all this started, and they quoted as like 2011 timeframe, I was 13 years old. So I was not working with SDN, so I can't speak on it. I bet someone else could give a better talk on it. But the goal of SDN was to enable flexible, programmable, and efficient networking, right? Especially as things started to move to the cloud and network virtualization started to really take off. But there was this company in the startup called PlumGrid, and they were really a pioneer in the SDN space. And they specifically wanted to build a bunch of network functions that kind of ran distributed on servers to provide network functionality. And there was this really, really smart man, Alexei Staroivatov, and I hope I pronounced that right. He was a distinguished engineer. And the way the story goes is he was troubleshooting a networking incident, and he realized that the compiler can't be trusted. Now, I'm curious how he just discovered the compiler can't be trusted. Like, it doesn't go into detail about specifically what the issue was, but I wish I knew, because I'm very curious about it. But what does anyone do when they run into an issue troubleshooting that they can't trust the compiler? Oh, let's rewrite it, right? So this man, who's an absolute king, invented his own instruction set based on x86 assembly, which is nuts to think about, just to get the kernel to verify an instruction set. So it's pretty amazing. And then from there, what happened was this sort of took off. He wrote it, and he was like, how do I get this implemented into the kernel? So he went and talked to Chris Wright, who's the CTO of Red Hat. And Chris said, hey, I suggest you bake it into the BPF project. Now, does anybody know why he would tell someone to, or tell Alexei to bake it into the BPF project instead of trying to merge it himself into the kernel?
Because it's going to be get rejected from the mailing.
Bingo. Yes, the kernel is a very protected space, right? And it's supposed to be stable. You don't want to go messing around with it. And even if it goes upstream, it's going to take years to take effect, right? So there's... What?
And Linus will yell at you.
And Linus will yell at you. Yeah, like the odds of him accepting that is probably very slim. So essentially what happened from there was they pushed up a patch set, and Daniel Borkman saw it. And Daniel Borkman was working at Red Hat at the time, and he was already working on existing BPF technologies. So he kind of saw this patch set, and this is the quote that he said. He was pretty much like,
hey, Thomas, I saw this patch set. This looks amazing. Can I work on this? The idea of eBPF and making the kernel programmable was immediately super interesting. Like a million light bulbs went off when I saw that. We actually met with Alexei, and we discussed how can we get this merged into kernel?
Right, a lot had to be refactored, a lot had to be reworked. And David Miller, who is sort of the network maintainer for the kernel, was like, hey, it's cool that you're pushing up this patch set. However, it's a little bit redundant, right? Like we just are about to merge in the Open vSwitch project into the kernel. The networking use case is kind of taken care of. You need to find a different angle because nobody's going to want to maintain this overhead, right? So he was like, rejected, go figure out a new angle at this. And this is where Brendan Gregg came in. Does anybody know who Brendan Gregg is? Beautiful. So this guy, I mean, I've only been really working with eBPF for like 7 months now, but ever since I started, this is all I see is this guy, right? So he worked at Netflix at the time, and he wanted to run Linux workloads in the cloud. And he was vetting a bunch of system kernel tracers, but essentially he couldn't find any that was really like full-fledged. Everything was sort of half-baked. There was a bunch of them out there. And he was like, I'm gonna have to rework these anyways. So he sat down with Alexei, and he was like, hey, I'm gonna make an agreement with you. If you guys build or integrate eBPF with K-probes, I'll write the front ends. And this is what we know as BCC and BPF trace, if anyone's familiar with those tools. And we'll kind of show them. But so they kind of refactored this, and they said, you know what? Here's a second use case. We're going to talk about kernel tracing. And once they started the kernel tracing path, essentially David Miller saw it and was like, you know what? It's a different angle. And it's already extending BPF. It's not something completely new. It's not going to break anything. So why not? And this is what he said. He just said, OK, applied. Thanks a lot, everyone. It was really that simple. And they wrote this whole long paragraph about like what this is and everything. But then from there, it really started to take off. It was a little bit slow at first, but Facebook actually started to leverage eBPF to build a L4 load balancer called Katrain. And this really took off. And honestly, Facebook's and Meta now is doing a lot more with eBPF. I just read that they're writing their own scheduler that's cutting down CPU percentage by over 5%. I mean, that's millions of dollars. Like, I can't even imagine how much money they're saving just from 5%. But it gave them 10x performance gains and 50 nanoseconds to process a packet, which is unbelievable, right? And then from there, really what happened was some of the maintainers of eBPF, like Daniel, like Thomas, they were saying, okay, well, we pushed up eBPF. How do we bring this to end users? How do we make this actually something somebody's going to use or be able to use? And that's when they built Cilium, which was an open source project. And does anyone use Cilium here? And you're probably using Cilium even if you don't know it. I think that's the reality. The GKE data plane's built in it. So it's pretty amazing, and you can see that here, right? So the GKE data plane, the version 2 of it, actually implemented eBPF and Cilium. So that just goes to show how quickly this has become adopted. But this kind of brings back to the point, like, what is eBPF in the first place, right? We talked about like how it solved the problem over time and like where it started. But essentially, it is a kernel technology that allows you to essentially inject or dynamically run safe and performant programs in the Linux kernel. And I think the key thing there is safe, because a lot of people are going to say, tell me you're going to push a program into the kernel. It's a horrible idea. But it is safe, and I'll explain why it is. But it's been used for a bunch of different use cases at this point. This is why BPF and eBPF kind of don't gel as much as you might think, because BPF was meant for like packet filtering and moving packets, right? But eBPF has really extended out into this completely different use case of observability, security, networking, and there's so much you can do with it. And the way this is kind of framed as an analogy is eBPF is to the Linux kernel like JavaScript is to like a static web page, right? Like JavaScript made web dynamic. eBPF is making the kernel dynamic because you can extend it, right? You can add more functionality and you can write code to be able to integrate with it. So let's go one step further and let's talk about actually what is eBPF. And this might seem daunting, especially if you haven't worked with it before. And honestly, it still is daunting to me. Even when I look at this, it's still pretty crazy. But let's talk about this kind of in steps here. So essentially, an eBPF program is event-driven. So right, an application reaches a certain point or passes a certain hook. These hooks are essentially syscalls. So who's a programmer here, or like a software engineer, right? So a lot of stuff we do, such as like opening files, receiving network traffic, it's all kind of abstracted in these programming languages, right? And what that does is it goes through the system call interface, right? So how the user space communicates with the kernel is through syscalls. And that's where eBPF programs pretty much hook into, right? So the way it communicates to user space to the kernel is through system calls. And it hooks into those, right? So something like a function entry exit, trace points, network events, so forth. And these are some hooks that you are going to see if you start to learn more and more about eBPF, which is like K-probes, U-probes, and a lot of technologies, especially in the observability space, are using both of these to be able to get tracing in terms of function calls, but also network performance. So K-probes will hook into the function or the kernel space, and then U-probes will hook into the user space to be able to trace specific functions like a Python program, a Go program, so forth. So how are they built? Well, eBPF programs, you can write them in C, and they mostly are written in C, but there's kind of tools that abstract this away from you. So there is something like BCC, and we'll look at a BCC program. But essentially, what Brendan Gregg did was he said, I'm going to take Python and Lua, I'm going to wrap it, so you can just inject a eBPF program in that, but you can also do the data formatting in Python and Lua. Because if you're writing a low-level language like C, kind of a pain in the ass to format that. So Python does a really good job with that. However, I think like any good technology, sometimes you don't even understand if it's running. And I think eBPF is going to be one of those technologies, and it kind of already is. It's going to be abstracted away from us. Like you already see projects like Cilium, Grafana Bela, if anybody's used that, to export and capture OpenTelemetry data and Prometheus data. Also like Falco. Right? So you have these products, and they're running eBPF behind the scenes, but you might not even know it. But if you wanted to write your own eBPF programs, you absolutely can. So essentially what happens is you use something like LLVM or BCC. It compiles that into eBPF bytecode, and then the eBPF bytecode kind of spits it into the kernel through syscalls, or hooks in. So how is it dynamic? And the reason I say dynamic is because essentially, it can be injected at runtime, right? So there's a BPF syscall, which is something that was built quite some time ago. But that's essentially how these programs, like using BCC tools, will kind of hook into it. But probably the question everyone's wondering is, how is it safe? If I'm just injecting something into the kernel, it's probably going to be pretty dangerous, right? Well, there's a few ways, and it passes through sort of two things, which is very, very smart. One is that it requires privileges, right? So like I'll show you when I run BCC tools, but like I do it in sudo. Or you have to have certain sys requirements, such as cat BPF. And especially if you're running something like Grafana Bela, you'll see that in the documentation. But also is the verifier. And the verifier is really the key component here. Has anyone read up on the verifier at all? Yeah, a little bit. So the verifier really makes sure that you don't write code that blows up the kernel in your computer. So it does things like checks to see if you have uninitialized variables, if you have infinite loops, if you have no dereferences to pointers, right? If you have no pointers, all this stuff that kind of breaks your code on a day-to-day basis, especially at a low level, it's going to make sure that you don't do that so you don't break everything. And that's why it's safe. But after that, essentially, it goes through a JIT compilation, just-in-time compilation, and it just translates that generic bytecode into the machine-specific instruction set to optimize the speed of the program. And that's actually why it's so fast, right? eBPF is extremely performant. And then I'm just going to show you guys, these are just some cool eBPF projects. Calico. I believe the GKE data plane before Cilium was actually running on Calico. Tetragon is a Cilium project as well. It's more for security. Bela in the bottom right-hand corner, that is Grafana's auto instrumentation. So one of the biggest pain in the asses in observability is instrumenting your applications and services. Oftentimes you have to either make config changes, you have to worry about dependency updates, make sure that there's parity there, and make sure that everything's actually working with that update. With Bela and with auto instrumentation, you can inject it without having to restart any of your services. Any of your servers, it just hooks into eBPF. It'll read red metrics, give you data, funnel it back up into OpenTelemetry format or Prometheus format, so it's all open standards. And then you can send it to any backend you want. You could send it to Grafana. You could also send it to any other OpenTelemetry compatible database. And just want to talk about the future of eBPF real quick before I jump into sort of like the, oh yeah, what's up?
So can you talk more about the traces in Grafana? Does it sit on top of the verifier?
What do you mean, does it sit on top of it?
So how do I visualize some of the connectivity and if I'm going through the,
Yeah.
if you talked about more on that, so can you just give me an insight on it?
Yeah, so like the way that it works under the hood is it actually deploys a uprobe. So what we do is we do kernel level tracing, both on the network side, but we also, if you're running something like a Go application, right, or Rust or C or Java or whatever, what will happen is you'll use uprobes to talk to user space to be able to pretty much say that's a span, right? And you can also do context propagation with that. So Bela does all that for you, but then it essentially says, okay, do you want to emit that through OpenTelemetry or Prometheus? The metrics will go through Prometheus, but if you want to do the traces, usually it's over OpenTelemetry format, and then you can send that into Grafana, and I can show you an example if you want to see it, like in Grafana, but you can just spit out there. You could also spit out to a different backend, right? If you want to use something like Logs.io, they probably accept OpenTelemetry, and there's a bunch of all those, right?
Right, but the dashboard helps. So I'm just trying to see if you can connect the dashboard with the traces. It's easy for me to view all in one panel.
Yes, exactly, and I think that's like the thing I'll show you is like when you do tracing in something like BCC tools that are installed on your Linux machine, it gives you data, but it's kind of hard to read unless you are really comfortable with like system level calls. So what Bela does is it pretty much interprets all that stuff happening under the hood and will just make it more human readable for you.
So I'll struggle with this. How do they coexist? If you're messing with the kernel to that point and you're changing behavior, how would all these tools coexist in the machine without stepping on each other's toes?
Oh, you're saying because you can have multiple eBPF programs running that don't interfere with each other.
Even if they're messing with the same calls,
Yeah.
file like the calls are doing?
Yep, definitely. Yeah, definitely. Like I know a lot of people who are running Cilium and Bela together. I know a lot of people that are running Cilium in something like Kunai, which is a new security open source project. Yeah, you'd think, right? Like I kind of thought that too, and then I read more on it, and I've heard from customers, no, they really don't run into issues with it. There might be edge cases to it, I just don't know about, and I haven't read about, but if you find them, let me know. Any other questions?
Just one follow on that.
Yeah.
So it sounds like no application has to coordinate with the other application. You just don't care what's running on it. You run your thing on there.
Yeah, well, because it can dynamically understand how your services are interconnected. So usually like something with Bela, like it'll understand HTTP calls and gRPC communication. So it'll be able to create like a service graph based on that. So if you do have a microservice architecture, right, and you have like service A talking to service B, talking to service C, right, it'll be able to make that communication through the syscalls. And then it'll actually make a map for you so you don't have to like try to figure that out in the CLI, right?
But isn't it the case like Alco is going to try to prevent certain things from happening that it doesn't think they are okay?
Yeah, I don't know that's true. I don't know the minutia of Falco, so it could be the case. I can't imagine that Falco would block other eBPF programs, but maybe. I would have to actually like test it out because I am curious.
It doesn't.
It doesn't? Yeah. So do you know why specifically it doesn't, or is it just like you've tested it and it?
Well, I mean, you can test it anytime because you can run Cilium and Falco together.
Right.
On the same device, but I mean, most of it's asynchronous, right, in the processing, like you said, right? It's event
Correct.
right on the hooks that are in there.
Correct.
I think also Falco in the container world, right, could dove up into secrets and namespaces, so it's actually going into not the host namespace, but the actual container namespaces.
Exactly.
So it's preventing those system calls coming from there versus coming from the other place.
Yeah, I'm pretty sure. I don't.
And then on the chaining, you like there are programs that chain, but if you're not chaining, like it only matters if you're trying to chain things. Like if you
Right.
wanted to do everything in the same event line of traffic, then you have to have some level of dependencies on. But it's not because
Sure.
of eBPF, it's just your programs have to know each other.
Right. Exactly.
So like Cilium can process like HTTP traffic, but you can run Pixie, Valin, and whatever,
Right.
all get in the same HTTP.
Yeah. Exactly.
But if you wanted to do it all in a chain, then you have to coordinate the programs like any program.
Right, and I've also seen people that have run, Cilium has a product called Hubble, and that's sort of their observability solution. And that allows you to sort of map network dependencies. But I've seen people run that and Bela at the same time. And those are two eBPF programs. So to answer your question, like, yeah, it doesn't. Like, I wouldn't know the nitty gritty of how.
But I think there is a different use case here because, you know, in the eBPF, you don't have this isolation. So basically, eBPF program A using something called maps to coordinate the data between kernel and user space. And there is this eBPF program B, which uses different maps, but they can interchange. You know, this program can access the memory map directly for this program. I mean, you can basically step on the other guy's shoes if you want to. There is no restriction from the kernel like in the normal user space program where you have virtual memory and all this isolation.
Makes sense.
You're much below this level.
Yeah.
Where you can, if you want, you can just directly mess with the memory map of the other program.
Oh, the last thing I wanted to just talk briefly about before I show you guys is the future of eBPF. So this is something I've read up on extensively, and I've kind of broken up into, really I think it's 3 different things, but I didn't put an image for one of them. So I think the first thing is cross-OS compatibility. Right now, obviously, it's just present on Linux. However, Windows is making some strides. Does anyone work for Microsoft here? No. Okay, so Windows is making very big strides with the I/O visor over there. So I think that'll probably happen in the short term, or like shorter term than you think. I think they're really making strides there. I think ultimately it might get eventually rolled out into Mac OS. Apple's weird, so who knows if OS X is going to block that kind of thing, but because I know they like to abstract everything away from everybody. But it is possible, and I really think the second part to that is that there's going to be organizations that are going to try to make this cross-compatible and make sure that everything you're doing in Linux you can do in Windows and you can do in OS X. And I think that's really going to be the big hurdle for eBPF, is that right now it's really supported in Linux, but what about Windows? Like, how does this translate over? How do a lot of the BCC tools, how do a lot of the BPF trace tools port over? That's going to be a huge problem for them, and I think they're going to figure it out though. And then the third thing that I really think is going to be the future is AI, right? Like we just heard it, and I think right now eBPF is great for like getting low-level performance data on like the CPU, right? And especially networking. But what about GPUs? Right? When we start to think about GPU output, and I think I read something that was like, the amount of data centers that are going to come up in the next like 10 years is a crazy percentage more than it is now. And it's just like, this is going to keep happening, and AI workloads are going to create more power, more consumption, going to cost more money. So everyone's going to be trying to find little ways to optimize that and save dollars, especially from the performance engineering side.
Uses that for, Facebook uses eBPF for optimizing their GPUs.
Really?
Well, if you actually look at how CUDA kernels are loaded, it's actually like 4 syscalls. So they're basically just monitoring the same thing, but they're monitoring the specific syscalls on them to see how long it's taking to do this, optimize stuff, where things are moving around, how much utilization they're actually getting. Like, so from the sort of kernel interaction and program interaction.
Yeah, like
they only write about it. They don't share the source code to it, so it's unclear what they actually do. But they've done a few presentations.
That's interesting. I would love for you to share that with me, because I found like, does anyone read like Netflix engineering like Medium blogs ever? I love their stuff, but I can never find anything on like Meta or Facebook on what they're doing. I wish they maybe they do publish it. Do they have their own like blog or something?
I just found a random search in
okay.
you and eBPF, and I found a random presentation.
Oh, awesome.
Delivered like 4 times by the same person.
Oh, that's beautiful.
Probably leaked.
Yeah, it might be leaked. What's up?
Today, in my world, there's a lot of hardware assisting dealing with packets, right? eBPF.
Right.
But it sounds like eBPF, you get to the kernel, and that's it, right? But there's no, can you go any lower? And I don't think
How much lower you want to go?
hardware assisting.
Well, I think the question actually is like, are there any technologies or products in the open market that are doing offload, right? Like, going back to eBPF or packet shuttling, Cilium, XTP. Are there anything, in the SmartNIC or DPU arena for doing offload of eBPF?
how are you defining offloading?
Right, so usually your data plane is hardware, right? Like
Sure.
Cilium is fast for a software data plane.
Yeah.
It is not fast for a hardware data plane. If you can offload that
Okay.
to custom silicon, then
Sure.
you can have hardware data plane with eBPF programmability. So I guess the question is like, is anybody doing in the open market
Not that
hardware
I-
offload?
Not that I know of.
Cisco is, that's why they bought Isovalent, right?
Yeah, so Cisco acquired Isovalent a few years back, yeah.
But there's no product today
Right.
as of, that does.
Yeah, in terms of like offloading a hardware data plane, I don't think so. I'd have to ask someone from Cisco. That'd be interesting. But yeah, so that's kind of where I see eBPF going. But honestly, you never know how these things shake out. So I just want to show you guys.
I think it'll be more usable for the masses.
More usable for the masses. How many more?
Or always consumed through stuff like yours.
I think it's gonna be abstracted. I think it's gonna be something that runs behind the scenes in a lot of technologies. I think like most I think like you already see so many technologies adopting it now, but I don't think anyone wants to write C programs. Like even like hold up. So let's look at one real quick. So let me open up my EC2 instance.
And then we'll try and get Don's talking as well. So
Yeah. I'll wrap up real quick. I apologize, Michael. So let's just look at the tools real quick, and let's look at like so like this is a BPF, or this is an eBPF program that's in BCC tools, right? So if we scroll up here, you can see that this is Python, but it's wrapping a C program into the Python. So you can see like, who wants to write this? Raise a hand. Oh, yeah, I thought you had a question, sorry. So like you can see here, like they're doing a lot of parsing to try to format data for you to be able to like make this user-friendly when you actually run exec snoop, right? So when you actually monitor that syscall. But you're still gonna have to write C programs regardless, and you can't get out of it. So that's why I think a lot of very smart people are gonna write these C programs for us, and we're just gonna be able to benefit off of them. But if you always wanted to go in and modify it and say, you know what, this doesn't fit my use case, I need to go a little bit more, that's why eBPF is awesome, because you don't have to use kernel modules, right? Nobody wants to write kernel modules, and they can break everything. So eBPF is really the solution for that.
Rust. Most of this stuff happens in Rust today.
Yeah, a lot of it does happen in Rust.
Actually, that's a good question. What happens if something that uses eBPF does break? Like if the KMOP breaks, oh boy. But if like something using eBPF breaks, like what's the blast radius?
Well,
Is there a blast radius?
I guess how would it break? That's the first question.
Yeah, sure. Okay.
I haven't seen it. I haven't heard a use case. Has anyone else heard a use case of where eBPF has broken the world?
I mean, no, but that's the danger is that you're in the kernel and you have a system crash.
And I think there's also a kind of like a misrepresentation. I think a lot of people thought the CrowdStrike thing happened because of eBPF. Like I've seen blogs. This is the only reason I say this, and I think it actually could have helped prevent it, probably not done it. And also that was just a horrible incident anyway, so forget about that. But yeah, so that's I know we're kind of over time, so I'll hop out. But yeah, if you guys ever want to talk about eBPF, follow me on LinkedIn. Love to talk more about it. I love nerding out about this stuff, so anything not working, I'm game. Thanks, guys.